presentation. As Luca mentioned, part of my current research is the preparation for the upgrades for the high luminosity LHC. So that's going to be most of my talk today. So this is the LHC timeline, right? It's a fairly busy plot. So that's the timeline, and that's halfway through 2012 the Higgs boson was discovered, right? So the question after this is, well, if you discovered the Higgs, what's left to be done? It's a good question, right? To me, the best analogy historically to this is with this quote from Michelson that is very famous, that all fundamental physics is done, and there may be like high precision measurements. It's actually a very long, it's like a commencement speech in some physics department. And he talks about the argon discovery and sort of basically we would call it intensity frontier nowadays. Right? I knew about this phrase. What I didn't know until recently is that actually been made 7 years after he made his experiment disproving the existence of ether. And that's, to me, is pretty amazing because, yeah, you can sit on something that completely abandoned physics and not doubt it, but still reply to what it will eventually do. Right? So nowadays, the reason it resonates with me is that we've discovered what appears to be a fundamental spin zero field with non-zero Bev, which I guess is the Lorentz invariant definition of ether, as if you can come up with it. So that we filled the universe with ether. That's what gives everything mass, right? This Higgs field, sorry, right? What is the standard model explanation for why we have that and why we have the spontaneous symmetry breaking? Well, the standard model explanation is that the mu square is less than 0. Right? It's basically saying that the standard model Higgs mechanism explains mass is the same as saying that Ginzburg-Landau theory describes superconductivity. It's true. However, if you dig a little bit deeper, you actually realize that there is a new force in the electrons at the long range, right? There is the carrier of that force, phonon, and that's what actually makes superconductivity. That's what makes a potential like this work for the superconductivity. So, if you like, any real explanation for spontaneous supersymmetry breaking will have to require new forces between standard model particles, and therefore new particles themselves. Right, so could be SUSY, could be something else. Right. So that is basically the agenda for this, right? So we're right somewhere here, right? So we're about a year ago, we finally achieved final energy and the design energy and luminosity of the LHC. And as you can see, there is a whole lot of upgrades that is going to come in. And the high luminosity LHC that I'm talking about is the one that comes over here, right? Turns out that you're going to operate at factor of 7 luminosity that you designed these detectors for, so you really need to rebuild them from scratch, right? There's been many studies done for this. This is in context of new physics searches in final state with lepton and 2Bs. And I will not go into the details, but basically this is the exclusion before the high luminosity LHC comes out. This is how it improves if you don't upgrade the detector, and this is how it improves after that. And this is very much related to supersymmetry and naturalness. Right, so you have to do some upgrades because your tracker dies. You need better B-tagging. You need to maintain the trigger. You need your colorimeters to work to measure the sequence. So when I say build new detectors, it really is building new detectors. There is very few systems in CMS which aren't upgraded for this, right? So we have new tracker, capable of triggering at 40 megahertz, which is going to be most of my talk. There is a new colorimeter with very interesting features, and then new extra muon stations, colorimeter electronics, muon upgrades, and so forth. And now, as of a week ago, right, we know that the fast timing is now officially part of the experiment. So that's going to be timing all the charged particles to 20 to 30 picoseconds, which is also nothing to sneeze at. This is going to be, I don't think people quite realize yet how powerful this is. So all these upgrades, you know, the motivation, the original motivation for them was, well, we're getting up in luminosity, so instead of interesting event with 20 pileup events, we're going to be having interesting events with 200 pileup events. You have to make more segmented, better detector. But you don't have to just stay with this, right? Once you decided to build something like this, you can actually see what else can you do that you haven't been able to do before, that we can't do now. Right? And this touches, you know, since I spent so much of my time looking for new physics, if you're looking for new physics at hadron colliders, your nightmare is the trigger, right? Because you have events at the LHC, the events come at 40 megahertz. You can save, well, right now you can only save 500 hertz, right? You have to decide in advance what kind of events you're interested in, right? And with new physics, it's the unknown unknowns that get you. So, you know, we have searched a whole lot of new physics, right? This is the old cartoon about looking for something under the lamppost. So this guy lost his keys somewhere there on the parking lot, but he looks here because the light is gone. So even if it's known unknowns, right? You still have you know, triggering on new physics at hadron colliders could be a challenge. Right? So that sort of comes to this point, right? So if you're going up to here at the end of the life of the LHC, well, we started, you know, a couple of years into it by discovering Higgs bosons. By the end of the LHC, we're going to have a good fraction of 1 billion Higgs bosons. Right? So this is a really big number. Right? So since I'm in Texas and in the school that gave our new energy secretary D in meats, I thought that I would brush up on my meats. So interesting Higgs decays are like great steak. Right? They're rare. Right? And 10 to the 8th Higgs bosons is exactly the kind of machine that you want to get to the rare. So this is an example of this important blind spot, right, related to the Higgs. Right, so we've been looking for dark matter for a while. It doesn't seem to be coupled to us by weak interaction. You know, the classic WIMP is kind of getting squeezed. We don't know how dark matter interacts with us. It may just interact with us gravitationally in the first order. But whatever this hidden dark sector is, right, we share a vacuum with it, right? And Higgs is the vacuum, right? It would be really strange, right? It would be some really interesting conspiracy if there's absolutely no coupling somehow between the sectors, because we do live with the same vacuum that is our Higgs. So, I mean, this can be small, right? But it would show up eventually at this exotic Higgs decays, right? Maybe at the 10 to the minus 5, 10 to the minus 6 level. Right? Still, right? I mean, once you have 10 to the 8th Higgs bosons, this gives you a lot of events to think. So, one of the standard, and there's an excellent review here of what kind of exotic decays Higgs could have. But one of the most popular ones that comes up in all kind of different models scenarios is that Higgs decays to two scalars, say 30 GeV. In this talk, I'll just assume that this guy is 30 GeV, and that goes to BB bar. Right? So if these decays are prompt, there is no hope. Right? The 4B standard model background is so big that this will just never come. However, if phi is not very long-lived, but a little bit long-lived, right? If it flies this far out, it's a zero. If you get these events on live, on tape, it's a zero background surge. There is nothing in the standard model that can keep it. So what's the problem? The problem is that it's 125 GeV, and even now, the lowest you can go with these displaced jet triggers, 450, 500. So you're completely blind. Well, you're not completely blind. You also can produce Higgs by the double unit, right? And then trigger on the muon, right? You start with the penalty of about 200. Right? So this is your fallback position. It's a little bit of that. I mean, also the muon trigger is going to work by electron trigger. So if you just look at the branchings, it's more like 150. But when all said and done, it's about. Right? So the question is, if we say that we can reconstruct tracks at level 1, can we detect that there is a little bit of a lifetime with these guys and compete with the fallback?
So the mass, this phi is what?
I'm going to assume 30 GeV, but it's.
And the branching fraction, you took it to be that your.
Right now, I will sort of have the benchmark that the sigma times branching of all this. So the branching of Higgs into 4Bs is going to be 10 to the minus 5, right? I mean, you can scale it up. So actually, Atlas has been surprisingly inventive with those things, right? So Atlas, well, at larger lifetimes. At larger lifetimes, you can get into sort of exotic problem, exotic signatures, right? So imagine that this phi now goes and flies all the way through electromagnetic calorimeter and decays in the H column. Then you have a jet that has absolutely no electromagnetic energy, which is rare, as you can see. This is sort of the ratio of hadronic to EM versus the decay distance. And you see that once the decays are after ecal, you see a very, very different jet, right? Atlas also has this air toroid muon system, right? So they actually can go even longer lifetimes and have less things decay in the muon system. Right? So, however, in terms of decay volume, you see you're sitting between 3 meters and 7 meters, or 2 meters and 3 meters, depending on where your decay volume is. So, if you look at where they're setting the limits, their proper decay length, or C tau, right, is all at the kind of around a meter, right? So this is the muon system, this is the calorimeter. It's sort of longish lifetimes, like this far. But because of this, and because they can build a trigger on this at level 1, they can get to a few percent branching fraction sensitivity, even with just their own bonding. There is a third competitor, which isn't exactly straightforward that this would be sensitive to it. But it is. There is an experiment called LHCb. It only instruments the forward region and supposed to study flavor. But the upgrade that it has for the high luminosity LHC is to completely eliminate the hardware trigger. So they're going to take a hit of about 30 right? Because they don't take the same luminosity as the big detectors. But all of these events come to the high-level trigger, and you can be inventive with it, right? I mean, this is just a computer. You can do whatever you want, right? So it's surely worse than the best CMS can do, but it beats W2 L mu associated. So, the push, right, is to get things to the smallish lifetimes, right? So lifetimes of the order of a few centimeters. So the trick is to find a way to pass the level 1 trigger, the hardware trigger, right? And you know, there was this great analysis in run 1 looking for pretty much that, right? Well, they scanned in the Higgs mass, right? That was, you know, all kinds of different H's, right? And you can see that if you assume H is a TeV, then you're setting limits which are tiny fractions of the femtobar, right? If you go down to 200, you're now just a tenth of a picobar, right? And at the Higgs mass, even in run 1, they already didn't have any sensitivity, just because you can't pass the hardware. So that's the challenge. So now, this is our upgraded tracker. So there are, it's lighter, faster, and cooler than the previous one. It now goes to rapidity of 4, which is great. But the most interesting thing is that all of these modules, so what you see here is tracker modules, they come in a very interesting geometry, right? So there are two kinds of modules, right? So the ones which were red and the ones which were blue. That's not particularly important for this talk. The thing is, as you see, both kind of modules have two sensors in them. These yellow things are the sensors. And you know, the fact that there's so many parts in each module tell you how complicated it will be to build this device. But these two sensors are not what, you know, people did back in Tevatron days or even Run 1 days, where you have like a little angle and you do a stereo measurement. No, those are sensors which run like this. They're really just stacked sensors that measure the same coordinate. And the idea is that if you have, so those two sensors, right, as the particles curl in the magnetic field, the low PT particles will curve a lot, the high PT particles will not curve a lot, and if you make an ASIC that sits there right on the module, right, you can actually discriminate between hits like this and hits like that. Right? And that is a great enabler, right? Because why didn't anyone trigger on the silicon at level 1 before? Because there's way too much information, right? So, and there is a lot of information because most of the hits are like this. They're low PT hits. So now if you're deciding right there on the front end that, oh, that looks like a hit from the high PT track, you get a factor of 50 or 100 in occupancy. And that's just enough to actually evacuate all the hits.
What's the latency between each layer, between the two successive layers?
Between two successive layers?
Yeah, those two layers. Like if you're trying to see if there's a hit.
Well, the latency between these guys is really negligible, right? Because basically, these guys and these guys are the signals coming to the same ASIC, right? The latency for the entire level 1 is going to be 12.5 microseconds, right? So, but that's for the entire thing, right? So these things hold the hit for 12.5 microseconds. But the trigger signals, of course, come out immediately. That allows you to actually trigger and then get all the rest of the hits.
How many such layers are there?
There are 6. So but there are a lot of overlaps here. So actually, if you look at the number of hits, you get something like 9 hits on average if you go this way, and more like 12, 13 if you go that way.
So they're all on the same base.
So each module has this combinatorial ASIC.
And then you, sorry, I have one more question.
Go ahead.
Then you combine between modules to actually truly decide.
Right, and but then that already happens on the back end, right? So the biggest hurdle, biggest technological hurdle was to actually evacuate those steps, right? And that is, well, I guess achieved because we have ASIC prototypes that can do that, and everything seems to be working, right? But what me and folks here and in other places were involved is how to actually construct a back-end algorithm to actually do the tracking, right? So that was done. We all demonstrated that we can do with 3 different technologies, custom chips, just commercial FPGAs, all that thing. So the question that I'm going to ask now is, well, this is all trained to be for prompt tracks, right? Can you make a trigger for the tracks that are a little bit off point? So the obvious thing that happens, right? So so this is the high PT track, this is low PT track. You see there are things there. The band is high here and small there. If you're off pointing, it all is completely wrong, right? You can get a good band for low PT track, and you can get a bad band for high PT. So the answer is that, well, you have to see what your sensitivity is, right? So I decided to decouple for many reasons we can chat about afterwards from the official simulation. And actually, for this type of stuff, you don't really need full simulation, right? You can make an idealized tracker parameterization with cylindrical layers and just see what's happening, right? So I have a definitions written out, but that's pretty much the quality of the. It's really as back of the envelope as it gets right now in CNS, right? So you have a track, right? It left the stubs, right? So on my loose side, I'm only interested in how many hits actually made it out, right? So this one, for example, will not make it because the band is too small, right? So I will not get a 6 stubs track, but I can get a 5 stub track. Or I can say, well, what kind of pointing tracks are we sensitive to now, right? And say that I will take my stubs and I will fit them to the track which is coming from the interaction point. And then I count the number of stubs which are within 2 strips from where my hit was supposed to be. Right? So, and if I do that, yeah, that I probably will get this track right now. Because obviously efficiency doesn't drop completely if I'm just a little bit off.
Yeah, but the PT will be different.
Well, the PT will be different, yeah.
Yeah.
But well, I mean, the PT of this guy may be fairly close, but yeah, I mean, basically biasing you're adding a wrong hit to it, right?
Yeah.
That it originates from there. But you can probably do something. You will reconstruct the track, and then maybe you'll refit it without the vertex constraint or something, right? But all your tools, all your pattern recognition, and all your track fits will kind of work. So then I can run this on jets, right? And this is generally, the jets from this Higgs decay, so it's somewhere between 40 and to 80 GeV. And you can see how things go. So the axis, so I basically go and I drop a jet at some coordinate x0, y0, right? And do this many times. And for each of this point, right, there is this impact parameter, x perpendicular, and then this longitudinal thing, which is this shift, right? So this is longitudinal, this is transverse. These are efficiency for the tight, demanding certain number of hits, right? So if I really want to get all 6 out of 6, you see that my rapidity sort of dies out at about a millimeter. My efficiency run out at about a millimeter, which still not so bad, but it grows very quickly, right? So if I do 5, you see I can go to the 2 millimeters. But it's definitely not great, right? If I go to loose, then things are much easier, right? So for 6, it's about a centimeter. For 5, which is still, our usual track selection cuts are 5 stubs. You see, you can actually do very well. You can go to several centimeters of impact parameter and still get the track. So the data that are coming to the back end will have hits that could reconstruct those. Our hardware right now will not reconstruct them, but. And then you can start playing with this, right? So instead of doing this track by track, because I'm a professor and I'm doing this as a hobby on my laptop, I can just do it as a jet parameterization, right? So jet is a jet is a jet. I can now drop a jet in of certain PT and see, and require it, for example, to have 2 tracks with 5 hits and 1 track with 4 hits. And that's actually already very rare because, it's a small area of space and it's very pile-up resistant, right? And you can see what's going to happen to a jet, right? So again, you get the same type of x parallel, x perpendicular type things. And yeah, for the tight, it looks pretty small. For loose, you see, we're now actually, for the reasonable PTs, you're going up to 5 centimeters easily, right? As you go to the lower PT, this becomes a little bit more challenging. So then I can go and actually fit those things, right? So if I fit those things, I get curves like this, right? So you can really see that this is within 5 centimeters, and then this is 2-3 centimeters. So that's now my tool. I now know how well I can reconstruct off-pointing jets. So now this is public.
I have a question.
Yeah.
Imagine we had a lot of pilot, then this technique won't work, right?
Oh,
Because
no,
it
it still will work.
Because even in the same module, you could have random hits that can make it both a straight track and a
No, but that's
for very high ones.
we are orders of magnitude away from that, right? So in fact, this is how one of the things why Atlas, for example, cannot do this type of thing, right? So what helps us is the 4 Tesla magnetic field, right? Because you need to bring the layers close together so that you wouldn't have that problem, right? But then you have to have enough bend to do that, right? And it turns out that 2 Tesla, factor of 2 in the magnetic field, that has a lot of advantages, right? So we can, even at 20 at the first layer at 20 centimeter from the beam line, we already have enough separation between 2 GeV track and 1 GeV.
And if I understand it correctly, now if you use this method, you can still get displaced vertex triggering
Right.
up to 5 centimeters.
Yeah.
And do you then let those events go straight to the buffer?
Now, well, we'll need to find out the realistic algorithm that can run with those latencies that can do that. But if we do, then yeah, eventually your trigger will be, I have 4 little jets like this that do not seem to point to the vertex. Right? And then if I have that, then when the level 1 fires, I reach back and grab corresponding things from the because I know exactly, right, that it took me 12.5 microseconds, I know exactly where in the FIFO to take limits. So, again, like you see, I'm trying to stay with the public CMS information here, right? So this is the trigger menu, right? So when do you fire this level 1, right, that you have, right? So if you have a single muon or 2 muons or a single jet and so forth, right? So, so the way this works, right? So this is the rate if you have level 1 trigger. This is the threshold, and the purple number is the rate if we don't have any track trigger at all, right? So this table used to justify the existence of track trigger, right? So obviously you win a lot for the muons, that's one way of doing it. For high PT jets, not so much, right? I mean, that's pretty much the same, right? For, say, quad jet, the one that we're interested in, yeah, that's a huge difference, right? Again, but that's because the thresholds are now lower, and the pileup makes the fluctuations large enough that right. So the problem is, right, and I think I have a slide about this later on, that in a large pileup, right, every once in a while you can get a small jet just because this vertex gave a little bit something and this event gave a little bit, right? And they're just fluctuations on the otherwise smooth cloud of energy, right? Could already give you a jet, right? And 70 is already at the point where you get it fairly often. Right? So, so yeah, there obviously the tracking helped because now you can associate jet with the vertex. Again, even with track trigger, as you see, the HT threshold is 350 GeV, way above the Higgs mass. It's completely useless. Okay. So what are the observations on that menu, right? One thing that was done completely backwards in my mind in that study was you reconstruct jets by starting with the most pileup sensitive detector, which is calorimeter. Right? It's much better to start with the tracks, and then if you see something in the tracks, confirm it with the calorimeter. Right? It also gives you more useful for analysis jets. If you want to detect that the jet is not pointing, you're mostly interested in the jets with a large number of tracks. Right? So for you, well, for me, a jet which is low PT but has a lot of but fluctuated high charge multiplicity is much more useful than the higher PT jet without many tracks. So, so that was one thing. That gives me a little bit of a handle, right, if I want to start jet finding with tracks. But the other is whether or not this whole thing is, I can do simple back of the envelope calculation. And actually just with Pythia and my parameterized thing, I can do pretty well, right? So I can get the high PT jet trigger fairly well. I can get the quad jet fairly quickly, right? So I basically, bounce off a few things, and basically my trigger that I will employ for all this will gives me fairly acceptable level 1 rate. Is just this, right? So I sum up. I do jet finding with just tracks, right? I mean, these are high PT tracks. You can't reconstruct all tracks, right? You start from high PT, right? So it's 2 GeV tracks. I slap some flat efficiency on it because there is some efficiency, and then require that the sum of all the tracks in the jet be above certain threshold, right? So I start with 20. For 20, I get pretty much the same rate as they get for the quad jet. And that kind of makes sense because usually 2/3 of the energy comes from the tracks, but then I'm starting with a 2 GeV threshold, and then there is a neutral pileup energy, so it actually kind of hangs out. This 20 GeV on all tracks should be about the same as the TSL. But then that's before I actually required things to be long-lived, right? So if I then look, so basically, that's my assumptions for what I was going to do, right? And I wanted to get this in a little bit better shape and on the archive by the time I came here. So the type that I described, I say represent what level 1 track trigger can do now. Loose is my dream. And then the pileup effects are, well, if you have 4 jets coming from the same z vertex, the pileup is non-existent. That seems to be the case, in my beating off Pythia from against the official menu. And for jets which are high above 70 to 100 GeV, well, at some point all these fluctuations of the pileup become small, right? So if you have a 100 GeV jet, it's a 100 GeV jet. Well, it's a high PT jet, it may be 90 GeV jet, but it's a jet. So these are my 3 assumptions, and these are my 3 triggers, right? So this is what we have right now. Well, variations of what we have right now. I can beat that by a factor of 2 if I have a lifetime tag. And then this is actually going to be interesting, right? So remember I talked about the things which decayed in the middle of the calorimeter, right? That was a very striking signature. So imagine now that the phi lives this much, right? It means that it still will give you irregularly looking jets, but they will have absolutely no from tracks pointing. And that's unusual.
What's the physical size of the tracking system?
It's this much, right? So the radius, the largest tracking layer sits at 108, and the ecal starts at 127. So in the end, when tracking fails, you still have this unusual object, right? The problem with this will be that tracks without jets are pileup noise, right? So you'll be battling against that. And that requires a little bit more simulation that I was doing. Right. So the long-lived tag, I just told you that I can go to the 10 GeV instead of 20 if I have a long-lived tag. To do this properly, you really need trackness reconstruction and all this. But I look at the total number of tracks in these events, which were supposed to be off-pointing, and there's a lot of them, right? And I only need, rate-wise, I only need a factor of 10 to 20, right? So I can easily get this with so many. I have some other plots in the backup that leads me to believe that, but
So
trust me, I can get.
This is a full simulation or what?
No, this is just my little parameterized.
Okay.
Well, it has some features, right? Like a flattened efficiency of
Sure.
about 90%. So, after I've done all that, I can actually run through my signal, which is my Higgs decays, and through just QCD as Pythia generates it, and ask what's happening, right? So how many events I get per 3 attoparts, right? Which is my ultimate luminosity, right? And I assume the sigma times branching of 10 to the minus 5, which is already pretty good, right? So if I just stick to the WH, and the offline, I'm really looking at the trigger at this point, because the offline, the moment you have a vertex which is off pointing and has many tracks associated with it, you're done, right? The standard model background to this is 0. So if you just stick to the WH, this is how many events you get. You get less than 2, right? So if you are sitting in the track trigger that we have, this tight quad 20 jet, this is what you're doing, right? And then if you go into loose tracks, right, and can lower this to 10 GeV by this lifetime tag, this is what you do as a function of the lifetime, right? So this is 1 meter. So this is actually pretty good, right? I mean, you get more than an order of magnitude on WH, and kind of order of magnitude on what you have currently. And then now if I do some simple estimates for how many events LHCb would have, I don't know how efficient it is or something. I just can calculate how often this phi will get into acceptance of LHCb, right? Since they don't have any hardware trigger, just look at every event, right? I do some maybe a little bit optimistic cuts in terms of acceptance, right? So the B quarks should have at least 5 GeV of momentum and so forth. But you get better than any of the existing solutions.
What was the pseudo-rapidity range that you had in your study?
So for CMS,
Yes.
it's the tracker volume, so 2.4.
So 2.4. Did you consider also using the higher lever arm you get if you go even further forward in the upgraded tracker to get even to higher C-tau?
You could, but your track trigger is really with the tracking modules, right?
Yes.
You can't use pixels in the trigger.
That's
And that
true.
limits you, because that's where the 2.4 comes from. That's where the tracker is.
But you still have all those extra end cap layers that you can use then. You even have more layers than just the number of the central layers, right? And
Well,
they're
that's
farther-
2.4, right?
Yeah,
So
yeah.
this is where you get.
All I'm saying, they're physically farther away from the beam spot, so
Mhm.
you could start to get the tracks in the end cap layers that you would not see anymore if you just had the central layers. So if you have more forward production, you could get higher lifetime C-taus. And still see tracks. That's what I'm trying to say.
Yes, but that sort of, unfortunately, it doesn't quite work this way, right? Because sure, they are more boosted, so they live longer, but that also means that their decay products are also boosted, and therefore pointing better towards the vertex.
Yes, but you still have those layers 5 and 6 at around 200 millimeters that will probably be hit if you have something like eta 2.4, and you could veto them and then take only the last layers.
Oh,
and
you mean
something like that.
you trigger on something that you have here and no
Yes.
hits there. Yeah, I guess you can do that. Yeah, because in the forward you are in this position where you have more hits than you really.
And they're farther away than the outermost layer of the barrel, so I think you could possibly extend your C-tau range by using more forward.
Yeah,
forward.
I mean, for my track trigger, I just assume that everything decays in a sphere of these 20 centimeters, right? Because that was, I didn't want to go into these layers, and then I know that at the C-tau of a meter, then these weird jets in the ECAL, HCAL, and these things come about. But in principle, yeah, there is nothing wrong with exploiting the fact that the tracker is actually long this way.
Yes.
Right, right, so you have an extra decay volume that you can utilize. Yeah.
Thanks.
That's, I'll have to think about it. So yeah, so the last topic that I want to touch is the trackless jets, right? So this is what a jet is in the pile-up environment, and that's what calorimeter thinks is a jet at the high pile. So, so the rate of fake jets is, this is why the rate of fake jets is highly nonlinear with pile. But on the bright side, it quickly falls with PT, right? So the figure of merit, I think, if you have a jet of 0.4 radius, the average energy flow into it is something like 15 GeV, 15-20 GeV, right? So if you calculate through sigma of it, you sort of get to 50-60 GeV. Again, this can be very reliably simulated with the toy Monte Carlo, but it's just a different toy Monte Carlo. You actually have to simulate all the events and do the proper pilot reconstruction. So for this, I just did it quick and dirty. So I just kind of assume that by the time you get to 70, 80 GeV, you suppress. You're still going to have a lot of fake jets, but you will suppress them, right? And then basically, you can go and just ask, versus jet PT, how many type tracks do you have, right? And then if you really require just one track, you get fairly quickly to something like a couple of %, right? If it's 2, then it's up, but then if you make a very small cut on the sum PT of these 2 tracks, you're back to a few %. So obviously, if you ask for 2 jets, this squares, right? It's seems like there is something to be had there. The problem is, if you have Higgs at 125 GeV, right? You can't really have 270 GeV jets unless there is a boost from initial state, right? So actually, if I just ask how often my Higgs to 4b will have 270 GeV jets, I arrive to something like 2.1%, which is 30 events, and that goes very quickly up if I lower the threshold. Right? So again, right? I mean, this is from the slide that I already shown, right? I mean, going in mass, we know that very, very quickly saturates. But you can run the numbers still, right? So this is the curves that I already shown, and this is what happens with these trackless jets, right? So they're insensitive here, and at the larger lifetimes they come in. And you see the 70 is probably the smallest threshold where this is realistic at all. And again, you're not really coming up anywhere near the efficiency you get with this loose string. Okay. Now, this is very mass sensitive, right? So I sort of stayed with the Higgs because that's the particle we know, and there's things, very generic arguments why new physics have to show up in Higgs decays at a very small level. But we can talk a little bit more, right? I mean, if X750 was good for anything, it reminded us a whole lot of how Higgs works, right? So one of the popular themes in all this X750 interpretations was this, right? So, well, applied to our stuff, the argument looks like this, right? So I have Higgs that decays to this phi through mixing with something. Well, first of all, if there is light scalar exist, right? What keeps it so light? right? I mean, you have the same hierarchy problem as you have with the Higgs, right? So what can it keep it so light? Well, it could be a pseudo-Goldstone, right? Well, if it's pseudo-Goldstone, then there is a symmetry breaking in that hidden sector, and there has to be an extra scalar that is associated with it, extra massive scalar. Now, it doesn't have to be nearby in mass, but it could be, right? And for 750, one had to be creative because the cross-section was big, right? So you had to involve vector like quarks or something like this. But in my case, I can just have this extra phi and extra x, right? So I either produce my little h at 125, and then through the mixing with this guy, it decays into phi, or I produce this guy through small mixing with the h, and then this guy with a large branching decays to phi. So what I get in the end is a peak at some other mass, right, that goes into the same final state. Right? And that's sort of, again, this is a very generic thing. There you can build a lot of models that give you that type of setup. Well, plus many other particles, but this is going to be a generic feature. So let's see how all this becomes, and things become exponentially easier with mass, right? So I ran it, I just doubled everything, right? So it's 250 GeV and scalar of 60. And it's still completely inaccessible by the HT triggers, right? Because the HT thresholds even now are 400 GeV, right? And now you see your expected events are in the hundreds, right? And still, right? If you look at the trackless jets do not quite keep up, right? So these are the 71s, which is a squeaker, and this is a 100 GeV one, and you see still. But, so this is a fairly important, sort of order of magnitude type case. So, question is, where are we going? Where do I go from here? One thing that I assumed is that once you do a track fit, the fake rate is small. That actually is true, right? I mean, if you look at the fake rate of all these algorithms that were proposed, you make, if you don't want to cut really high on the track quality, you get maybe some fakes at a very high PT. But there are so many low PT tracks that you don't really get a whole lot of fakes. Plus, we're asking, when I'm doing jet finding, and this is one of the reasons to start jet finding from the tracks, is that I now have 3 tracks that are originating from the same point and pointing approximately the same way. The fakes are going all over the place. So that, I think, is not too bad in an assumption. Right? The thing that I worry about is that when I say I vertex and say that they're all originating from the same point, well, I kind of magically assume that I still keep the vertexing in Z. Right? At some point it will break, right? I will need to make an extra effort to project these jets to a common Z position. And that is going to cost me in time and effort. Right? So, again, a little bit more toy Monte Carlos, I think can describe it. It sounds like something that is described, right? So I think the most squishy thing out of what I talked today is this trackless jets and how well you can do with trackless jets. That's just because it's hard to predict without proper simulation what is the calorimeter fake rate. So, so this is it, right? So we're planning substantial improvements to their tracker. I actually don't know how good Atlas is going to be. Atlas is doing something completely different, right? They can't do exactly what we're doing, but they can. But they have 2 hardware triggers. They have level 0 and level 1, right? So I'm kind of pissed at them because I go and say, hey, CMS is going to trigger at level 1 for tracks. And they say, Atlas is also going to trigger at level 1 for tracks. But they start numbering their hardware triggers at 0, and we're starting at 1. So the way this goes, there's level 0 knocks the rate from 40 to 1, and then they have another that goes from 1 to a few hundred kilohertz, right? It is possible that their hardware track trigger could make similar things and benefit the long-lived part. Right, and then of course there is the LHCb, which is just brute force thing that you sacrifice 1/30 of your Lumi, but you have all the events to play. So yeah, so although we gotten into this game to just keep detectors working, we shouldn't stop at that. This is a very unambitious goal, right? Some of the devices, some of the technology progress that we've made is pretty awesome. Right? And we should just try to see what kind of new physics you can do with this, right? So this was just sort of one example of what kind of cute things you can do with this. Right, so the killer is, of course, is if you not just build the timing layer, but also put it in the level 1 trigger so you can match tracks with, and now your tracks come with 30 picosecond timestamps. Now you're really.
So what's the situation about that? I mean,
Well, there was a proposal to CB, right? That was accepted.
Right.
So now there is a new subsystem in CMS called picosecond timing, right? So they have technology for the barrel. They kind of have technology for the end cap, and at least they have plans. In terms of putting it in the trigger, it's a lot of information to evacuate, right? So you talk with some people and you say it's crazy. You talk to some other people and say, I mean, you're dealing with the surface of the cylinder, which is 110 centimeters by 3-4 meters or something like this. Right, and it's covered by 1 centimeter square thing, so this is your number of channels, right? And those are not binary things, right? I mean, these are, you're basically getting a little oscillograms of what they see, right? So it's a lot of information. Whether you really can realistically put it in the trigger is weird, but that's exactly, the way I phrased the question is exactly what's wrong with the system, right? We shouldn't be deciding these things based purely on technology, right? We should ask ourselves, do we get extra physics if we do that, right? And if we do, we should decide whether or not we want to spend another $2 million doing this. I think at this point, right, we have these approaches to triggering. We know that unambitious, well, what used to be very ambitious thing now seems unambitious. Let's see what kind of extra physics we can do if we make it a little speedy. So that's what I have to say.